So today we're going to be looking at chapter 2, and we're going to be talking about water and aqueous solutions. And we have a couple of learning goals that we're going to focus on. So we're going to look at what kind of interactions occur between molecules. We're going to target why water is a good medium for life. And we're going to explore nonpolar moieties, or types of chemicals that aggregate in water. And then we're going to look at how dissolved molecules can alter the properties of water. And then the next time, we're going to take a look at the behavior of weak acids and bases and the way they behave in water. And then we're going to look at how buffers work and why we need them. And then we're going to examine how water participates in biochemical reactions. So if you take a moment and think about the water you consume on a daily basis. So think about the number of maybe glasses that you drink, or the actual volume measurement, whether that's in milliliters or liters that you drink on a daily basis. And consider the following. We're made up of about 65% water, and your body loses 1.9 to 2.4 liters of water per day. And so because water is the primary constituent of things like blood and cytoplasm, it's important in the lubrication of joints, and it's what we use for heat exchange as well as how we solvate other polar molecules. It's pretty reasonable to say that the more water we have, the less kidney stones and sometimes cancer, as well as other types of disease states, are likely to occur. Now, is it possible to have too much water? Absolutely. So if you actually take a look at the charts that are given, there's total water consumption. So that's how much you should be drinking on a daily basis. And again, that's in ounces. And then there's also the total body water as a percentage of your total body weight. And you're going to also notice that that too changes depending upon your respective ages. And if we think about, say, for example, our water intake, so we drink water, and that's roughly 1,200 milliliters per day. And there's water that's found in food, which is, again, pretty significant, at 1,000 milliliters per day. And then we get a little bit of water from our metabolic oxidation of food. So that gives us a total of 2,500 milliliters per day, or 2.5 liters. And then if you think about that water output, so your urine and skin and lungs and sweat and feces all contribute to the loss of water. And so if we think about the replacement of that and the ongoing need to drink water, one of the things that should be immediately apparent is we can quickly, if we don't consume enough water, get to a place where we have some percent loss of body mass. So 0% is normal heat regulation. That's what our body does if we have the right amount of intake for the right amount of outtake. If you think about 1% loss of body mass, that's when our thirst gets stimulated, and it's when our heat regulation starts to diminish. If you're in the 2 to 3% range, that's a significant decrease in heat regulation. And what's crazy is that by the time you get to 4%, you actually see a diminished ability to exercise by about 20 to 30%. And then if we go all the way out, right, to say 7%, that's where we see collapse likely unless we stop that activity or significantly replenish the water that's lost. And so where, you might be wondering, does all of that water go? What is it that we do with that water? Where does it go? And so if we think about our total body water, so let's say the volume was 40 liters, 60% body weight. So 25 of those 40 liters would be found in our intracellular fluid. And then our extracellular fluid really has two components. The extracellular fluid is made up of plasma, which would be about 3 liters, and then our interstitial fluid, which would be about 12 liters. And so you can actually see the 20% of our extracellular versus the 40% of our intracellular. But you might be wondering, okay, well, it makes sense that you would have water in both of those places, but what does that water actually do? And so let's take a moment and look at the different ions that are found and their relative total solute concentrations. So how much of them per liter do we see in these fluids? So for example, if I take a look at sodium, there's a lot of sodium in my extracellular fluid. So in blood plasma, in interstitial fluid, there's a significant amount of sodium. Whereas in my intracellular fluid, there's actually not as much sodium. Now, if I compare or contrast that with potassium, Potassium, there's a significant, again, portion in the intracellular fluid, whereas now in the blood plasma or my interstitial fluid, there's significantly less potassium. And so as you go across and think about some of these ions, as we explore in more depth, it's going to start to become obvious that it's really water that allows there to be different concentrations, and it is in fact those different concentrations that can result in cell signaling and other necessary processes. But today we're going to focus on hydrogen bonding and other types of non-covalent as opposed to covalent bond interactions. So Linus Pauling really foreshadowed this when he said that the methods of structural chemistry are further applied to physiological problems. It's going to be noticed that there's a significance towards these hydrogen bonds and that they're important for physiology and probably more so than any other structural feature. And so we're going to explore in a little bit more detail what it is about hydrogen bonds that makes them so special. But before we go forward, I want you to take a look at this image. There are a couple of things that are shown here. One, we show the electronegativity difference between oxygen and hydrogen. So oxygen is going to be partially negatively charged. That's what that delta symbol means. And then hydrogen is going to be partially positively charged. And so you're going to notice that there's an orientation where the hydrogen is lined up with the lone pair on the oxygen. And it's the relationship between those two that constitutes a hydrogen bond. The hydrogen is the H bond donor, and the electron pair on the oxygen is the acceptor. And you're going to notice that water is sp3 hybridized. That's why we see that 104.5 angle. And really, it's a dipole-dipole interaction that we're going to explore in a little bit more detail. And we aren't going to be surprised by the fact that we see significant and extensive H-bond networking in solid and liquid forms of water. And this is what leads to a variety of properties of water, like high density, high boiling point, high heat capacity, high dielectric constant. So let's take a moment and explore a little bit of those properties. One of the first things you're going to notice is if I were to take a solute like sodium chloride, so table salt, and I were to dissolve that in water, one of the things that would happen is that there would be this solvation effect where water would surround my ions. So in this case, the hydrogen on water would surround the chloride and orient itself towards that, whereas the oxygen on water would surround the sodium, orient itself around that. And so that's how we would actually hydrate or solvate this salt. But if we think about that in terms of non-covalent interactions, what's really happening? Is it charge? Is it some other type of dipole interaction? What is it that allows water to solubilize salt? So we're going to explore in a little bit more detail 4 types of non-covalent interactions. We're going to look at ionic or coulombic interactions. That's where there are permanently charged species, like the positively charged sodium, the negatively charged chloride. And then we're going to look at dipole interactions. So this is the equivalent of a hydrogen bond, where you have uncharged but polar molecules. So for example, water is polar because of the electronegativity difference. And so that's what allows there to be a hydrogen bond between water, which donates the H, and something that has a partial negative charge like oxygen or nitrogen. Then we're going to look at van der Waals interactions. So these are weak interactions that are between all atoms regardless of polarity. And they have both attractive or dispersion and repulsive or steric components. And then a little bit later on, we're going to look at the hydrophobic effect, which is how water molecules order themselves around nonpolar substances. But before we go further, I want you to think about the fact that really this is force at play. So if we think about Coulomb's law, right? Charge on one times charge on another divided by the radius squared. And so that's going to be mitigated a little bit by a proportionality constant that for nonpolar organics is going to be somewhere between 1 and 10, but for something like water that's polar is going to be about 80. And so we can calculate the force, and that force is inversely dependent upon the distance. So ionic interactions are going to be relatively short range, only 10 to 40 nanometers in aqueous solvent. This is important because it means that for intermolecular interactions, for example, for hydrogen bonding, they have to be close in order to have maximum effect. And so that's true for charge, and charge dipole. Now, if I think about dipole, this is what allows me to solvate polar molecules. So hydrogen bonds are this special type of dipole-dipole interaction. And it's, again, that lone pair and the positive charge of the hydrogen. So in this case, I'm looking at my hydrogen being my donor, the oxygen being the acceptor. That's between neutral groups, but I can also see it between peptide bonds. And then the ionic interactions that we talked about, so charge-charge interactions, might say, for example, between the positive charge on the nitrogen and the negative charge on the oxygen. That would be an attractive interaction, whereas I could also have a repulsive interaction if I had like charges. And then we're going to talk about hydrophobic interactions, which is where I can have two atoms that are in proximity that kind of can change their interaction with each other. That's our van der Waals. And then water is just kind of the ordering around these non-polar. So that's kind of the landscape that we're going to start to explore in a little bit more detail. And so here you can actually see several examples of both hydrogen acceptors, which is the lone pair on a more electronegative atom than hydrogen, and then our hydrogen donors. So it's pretty common to see oxygen and nitrogen as hydrogen acceptors. And it's not uncommon to see alcohol, this functional group that we see here, as the hydrogen donor. And if we think about maybe a little bit more explicitly some examples of that, you could actually see between the hydroxyl group of an alcohol and water, you would see hydrogen bonding. You could actually see it between a carbonyl group of a ketone and water, and then between, say, for example, peptide groups, or between complementary bases of DNA. And these are all examples of where hydrogen bonding is found in living organisms. But I want to go back to a moment to this idea of attractive and repulsive forces. So I talked a little bit about Coulomb's law, right? You have a constant, and then you have these charges, which are measured in coulombs. And there's a distance between those charges. And you might be thinking to yourself, well, that's all very well and good. Why does it really matter? And it matters because the force is what determines, right, whether it's an attractive or a repulsive interaction. And so I have two kind of diagrams here that I want you to take a look at. So if we're thinking about repulsive potential, right, so how likely is something, right, when it's near to another atom to be repulsed? That's this dashed line that we see here. And then we also have to ask the question of, well, how likely is it to be attracted? So obviously, if they're like charges, they're very, in most cases, going to be, right, repulsed from each other. But what if they're opposite charges? Well, they're going to have some type of attraction potential as well. And then the reality is that whether or not a bond occurs between these two is going to be dependent upon, right, this curve that we see here, where there's some ideal sense, right, of both the minimum energy that's required and the maximum energy that's required in order for that bond to exist. And so if we parse that out a little bit more, you can see here, right, if I have electron clouds overlapping and they're too close, right, there's going to be some type of repulsion. And likewise, right, if they're close enough, there's going to be some form of attraction. And if they're too far apart, there's going to be very little or no attraction. But what's ideal is this equilibrium position where I'm balancing repulsion and attraction, and that's what determines bond length. Now, if you think about that perhaps in the context of the hydrophobic effect, really what we're looking at is entropic considerations of water. So water surrounds polar formation, and it's a tight hydrogen bonded network. So there's going to be a net decrease in entropy. Whereas if I have clustering hydrophobic molecules together, the actual amount of water molecules is going to be decreased, so my change in entropy gets maximized, and it really comes down to thinking about surface area versus volume. Now, from a dispersion standpoint, right, part of what I'm thinking about is water becomes highly ordered at the edges when it's near something that's nonpolar. And that's due to this interaction of force versus separation distance. And so when we think about something that, say, for example, is hydrophilic or loving water versus hydrophobic, fearing water, or something that's amphiphilic, which is true of most biomolecules, that it could be either or, then we need to kind of have an understanding of how much distance really impacts that interaction. So here's a big picture view of that. So if I'm looking at intermolecular forces, so the forces that are between molecules, as opposed to intramolecular forces, which are the forces within molecules, I can actually see, right, the units in terms of kilojoules per mole of interactions. And you can see, right, weak or moderate, right, our dispersion, dipole, dipole, ion dipole, or hydrogen bonding that we've been talking about. And then intramolecular, so ion-ion or covalent bonds, are much stronger than what we're talking about in terms of these intermolecular or non-covalent forces. But how much of that is really dependent upon distance? Let's take a look. So you can actually see the distance dependence here. And you're going to notice that ion-ion is r to the negative 1. So it's directly dependent on 1 over r. Ion dipole is 1 over r squared. Dipole-dipole is 1 over r cubed. Dipole-dipole rotating is 1 over r to the 6th. And so there's also the induced dipoles that we can take account for as well. And then there's dispersion and there's hydrogen bonding. Now what's interesting about that is that you can actually see then the magnitude, right, of the interactions themselves. And so that becomes important when we think about things like membranes, right, where the hydrophobic effect is going to create our lipid bilayer, or in proteins where a hydrophobic effect drives the creation of a protein core, or in DNA where the formation of the double helix is dependent upon those bonds and that specific interaction. And so if we think about this in terms of where does it matter, so in carbohydrates, hydrogen bonds are a significant contributor, whereas the hydrophobic effect is more minor. In lipids, we would say that hydrogen bonds are fairly minor, but the hydrophobic effect would be major. And then in proteins, both hydrogen bonds and the hydrophobic effect have significant influence, as they do for nucleic acids. So now if we think about the hydrophobic effect, maybe with a visual to help us get a sense of that. So the dispersion of lipids in water. So everyone knows that oil and water doesn't mix. Well, why is that? Well, each lipid molecule has these forces that surrounding water molecules, right, respond to and become highly ordered. And so essentially because there is this interaction, right, you see these clusters of water molecules that have relationships or reactions with each other, right, and then they're also highly ordered, right, to form what we think of almost as cages around hydrophobic alkyl chains. And if we think about that perhaps in a more detailed setting where maybe we have an interaction between, say, for example, a substrate and an enzyme, right, we can disorder then the water and displace it by the interaction between the enzyme and the substrate. And so there's some type of stabilization that occurs, whether that's hydrogen bonding or ionic, or some type of hydrophobic interaction. And so when we think about this in terms of the way that that impacts hydrogen bonding, part of what we want to recognize is that hydrogen bonding is going to influence freezing point, boiling point, vapor pressure, or osmotic pressure. So when I dissolve a solute in water, it's going to change the properties of that solution. And if you think about the things that are soluble in water, whether that's an ion or a gas or a small polar molecule or a large molecule with many polar or ionic groups, right, we can actually think about the way that those groups then are going to interact, right, with each other and with water. So that's where we're going to leave off today, and we're going to pick it up again for part 2 shortly. Thanks again.